Hello everyone. In this video, we'll be solving problem 111, minimum depth of a binary tree. The problem statement is, given a binary tree, find its minimum depth. The minimum depth is the number of nodes along the shortest path of the root node down to the nearest leaf node. A leaf node is a node with no children. If you look at example number 1 to get a better idea about the problem statement, with this structure, the shortest path is 3 to 9. So the output is 2. This being the first level and this being the second. 9 is the leaf node because it does not have any left or right legs. Similarly, 15 and 7 are also leaf nodes, but if we calculate the depth of this 15 and 7, the output will be 3. And the problem statement is asking us to return the minimum depth. Hence, we'll return 2. This is a very easy problem. It should not take too much time to go to the whiteboard and understand the solution. So now let's switch and talk about how it can be solved. To solve this problem, we use DFS, which is depth first search approach, to iterate through all of the nodes, tabs on the depth at each node until we figure out a particular node is a leaf node. And once we encounter a leaf node, we'll compare the corresponding depth to the max depth, and whichever is minimum, we'll save it and then continue with the rest of the nodes. Let me show you with a couple of runs to explain how this will work. Starting off with the root node 3, we'll go to its left leg, which is 9. For 9, the depth will be 2 because the depth for 3 is 1. So we incremented it to 2 for node 9. Now we'll check, is node 9 a leaf node? It does not have a left, it does not have a right, so yes, it is a leaf node. So we'll compare this depth with the minimum depth that we have saved, and whichever is the minimum will be saved. So 2 being the smaller value, it will be saved into this minimum depth variable. So the new value is 2, and we'll resume the iteration. So we'll move on and go to the right side of root node and check if it is a leaf node. It is not because it has both left and right legs. So we'll go down the left leg. We are at node 20. Its corresponding depth is 3. Is this a leaf node? Yes, it is a leaf node. So we'll compare D against the minimum depth so far. Because the value is greater than the current minimum depth, we don't have to replace anything. And we'll move up to 15 and look at its right leg, which is 7. It is also a leaf node and its corresponding depth is 3. Compare it against to minimum depth. Minimum depth is smaller, so no change needed. So we'll just ignore and resume. As we have gone through all of the nodes, we will conclude our iteration and return this variable. With this approach, our time complexity is O of n, where n is the number of nodes in the binary tree and the space complexity is O of 1, as we are only using this one variable to maintain the minimum depth. I hope you were able to understand this solution. Let me show you how we can implement this using C#. Here is my C# solution. I have maintained a class level variable called minimum height and setting the default value to int32.max. In the main method, I am first checking if the root or the input is null. If it is, then I am returning 0. Then I am calling this helper method, passing the root node and the current depth. In this method, I first check if my root is not null and height is less than the minimum height that we have calculated so far. If either of the conditions are not met, then I am exiting out of the loop. Let's say if both of the conditions are suffice, then I'm checking if the node is a leaf node. If both of the left and the right legs of the current node are null, it is a leaf node. So I'm calculating the minimum height. So the height that I have received as an input, I'm incrementing it by 1 and comparing it against the minimum height I have calculated so far, and whichever is minimum is being saved in the minimum height variable. If the node is not a leaf node, then I'm calling the DFS method again, passing the left leg and incrementing the height. And on the next line, I'm passing the right leg of the root node. After this entire iteration is complete, I will have the minimum depth saved in this minimum height variable and returning it on this line. This code, when submitted on LeetCode, beats 100% of the submissions made so far in terms of runtime complexity, and in terms of memory consumption, it beats nearly 31% of the submissions. Thank you for watching this video. I hope you were able to understand this explanation and the solution. If you have any questions, feel free to reach out to me. The link to the source code is available in the description below. Feel free to check that out, and I will see you in the next one. Thank you.